And we are live with the closing keynote of Meeting C++ 2020. This took me a long while to think about who and why and which topic should the final keynote in this year be. And when I got into thinking that C++ 20 actually is a 2020 release, my decision was pretty quick and clear that I'd like to have Gaby as a keynoter because he had fundamental influences on that standard and is a really good speaker. And so I'm really happy to see this keynote. And so I don't want to wait any longer for this. So please, Gaby, go ahead.
Okay. Good evening, good afternoon, wherever you are. I'm very much happy to be here, to be doing this live. I was quite pleased to be honored to be asked to give this keynote. I know C++ 20 is around. You have heard a lot about it. And what I wanted to talk about today is how you can use the tools that come with C++ 20 to make your applications much better, safer. Safety is something that is a topic that has been coming over and over again, and always people ask, what is C++ doing for safety? Have you heard about Rust? Should we use Rust? It's like, no, C++ has all that you need for now. So we have heard a lot about modules, concepts. What I want to emphasize today is just key ideas that you can use with modules, you can use concept, and how your compilers can support those fantastic language features that comes with the language. So the first modules, I guess an overarching theme of both modules, concept, and other functionalities that come with the language is that to get the benefits, the most benefit from them, you need to bring up the structures that underlie the foundation, the architecture of your software. If you have a messy code, module won't save you. If you have messy code, concept won't save you. To benefit from concepts or modules, you have to elect to practice hygiene, like to think really hard about the structure of your code, what you want it to be, as opposed to just, typing code and then thinking later, which is something you can do in some other context, but not really in the context of large-scale programming. Large-scale programming, you really want to think about the components, how they go together. There are a lot of tutorials, and I've already given, 5 talks on modules themselves. So I'm not going to get deep into that right now. I'll come back to that later. The other topic of the talk is concept. Here, the interesting thing is to show you in concrete code how I personally use concept to help me structure the code, think at large, manage complexity. The examples I will show later in the talk are from real world code. One of the software that I write on daily basis is the Microsoft Msvc Compiler. So it's a compiler that shipped that uses concept in itself, uses elements of modules and a bunch of other C++ 20 goodies. So this is coming from the trenches. This is not abstract ideas from untested ideas from some blue sky research. This is real stuff. So again, to get the most from concept and from modules, you need to bring out the structures that underlie the problem that you're trying to solve. So the problem I'm going to discuss and then try to show you how I solve it in a shipping product that many of you are using is when you try to compile module, you want to use modules, for example, your compiler would produce what we call a module build module interface. You'll say BMI. The problem is when you say BMI, it gets very confusing because it means something else. So here I'm saying module interface build artifact, just to emphasize that I'm talking about module interface and build artifacts. So what are they? They're generally produced by your compiler when it is translating your module interface unit or a header unit. And the reason why it usually does that is it tries to remember the work that it is doing so that it doesn't have to do it again and again. This is one of the problems that we have with header files today, which is that include is just copy and paste, and the compiler gets to do the same work over and over, and that's not very much green computing in any sense. So this is not, so the build artifact is not something that's standardized by the C++ standard. It is not. But it is an implementation strategy that is adopted by almost all implementations that I know of C++ module, which is why I'm talking about it. The other thing that it does is it encapsulates the semantics of your module interface or your header unit, your header file that you're trying treating as a header unit at the point where it was processed, so that when that module is imported, there is no disturbance. There is no macro, leaking into the processing, changing the semantics of anything else. You can be very confident of what the semantics of that source file is at the point of import. Okay. There is a typo here. So they are compiler dependent, not compiling dependent. They are compiler dependent. One of my goals for next few years is to try to get C++ implementers come to agree or realization that even though each compiler has its own implementation details, it makes immense sense for the C++ community to have a common ways of treating those implementation dependent entities. So it could be through a set of APIs, some kind of binary format, something that is common to, commonly understood by C++ users without imposing undue restrictions or burdens on the compiler writers themselves. And I think that is possible. And I will explain near the end of the talk how to get there. So why am I making a big deal of them? I think they are very important. They are very useful. If you want to understand, or you want a tool to understand a C++ header file, you need a C++ frontend. There is no way around that, because you need to do overall resolution parsing, that involve overall resolution, that involve compile time evaluation, that involve template instantiation. You need the whole schmilblick, right? But the interesting thing is that the metadata that a C++ compiler produces while it is processing your header unit or your module interface unit doesn't really require a C++ compiler to process again. So the opportunity here is that you use your C++ compiler once to produce this build artifact once, and then it can be consumed now by a lot of tools that do not need to be C++ compilers, do not need to be in the business of being C++ compilers. And there are many of those, right? Including programs that you write themselves. If you want to do some kind of runtime introspection, you need some information about something you wrote. You don't really need to link your C++ compiler into your executable, right? So that gives you a mass, I would say, a democratized access to the high level abstractions of C++ without, again, having to require a C++ compiler to do that. And you can use them for developer tools that need some kind of metadata about the entities that are in your program. So if you want to have some kind of safe runtime introspection, the information is there. You just need to point your program to that file and have ways of going through, sifting through the data and getting what you want. If you're doing distributed computation and you start computation here and you want to distribute data to stuff, you need a way of marshalling the objects, running on one machine to another machine, right? So if you use data abstractions, that's the way we tell people to do in C++, you need a way to describe the memory bits in a way that is structured, can be sent over a network, reconstructed on the other side, and put in memory and worked on, right? And if you're like me, you work in an environment where you can't just use one language, and it will be nice, right? But rarely can you just use one language. You use multiple languages, systems that need to interoperate with your C++ programs. Then these metadata actually give easy access to that sort of interoperability. Like you want to generate binding to Python. Today, the way we do binding is you declare your function as extern-C to escape mangling, and you carefully try to avoid any data type class that may be considered too complicated, right? You restrict yourself to int, double, and something that's kind of predictable, which makes it very bizarre or ironic in the sense that here you have a language that gives you access to efficient high-level abstractions. Yet you have to reduce yourself to the most unsafe and lower level part of it if you want to talk to someone else. It is possible to use the higher level, the safer part of it, if you have access to these data. This is why these things are useful. This is why I would love to see the community rally around, developing something that can be produced by all C++ compilers that I use on a daily basis. So a couple of years ago, while I was working on modules, I did write a short paper explaining why I believe modules are actually a tool opportunity. I would encourage you to get that paper. It is a short read, a couple of pages, and gives some ideas about where to start. And one of the things that I'm committing myself to is in coming months, start pulling out, making more real some of those ideas. And I'll need your help, everybody's help. So the Microsoft compiler, just like Clang or GCC, produces one of these BMIs, and the Microsoft compiler calls its metadata file an IFC file. Here, for the first time, I'm going to describe a little bit more in detail what these files look like and how complex they are and how I got to tame the complexity. And once the complexity is tamed, everything is simple, and you can even write your own scripts. Like you can write your Python script, your Ruby script, JavaScript to dissect these IFC files. So you don't need a C++ compiler to go and try to understand what is in there. You can use any computing language that allows you to look at binary files. So like I said, the IFC file is used by the Msvc toolset to represent the metadata when the compiler is processing a module primary interface file or a partition interface file, or what I call an internal partition file. So what is an internal partition file? It is a module partition file that does not export anything, but that can be imported in other module units. Its usage is rare, but it is supported. And the IFC file, it says file, but it really is a binary format. It is structured, and the principles used to devise these structures are the ones that guided the work that I did with Yannis Trustrup on the internal program representation for C++. It's a small library. It's on GitHub. You can go there and clone it. I've been doing some work there. I expect to do more there. This binary format, it's relatively compact. One thing that I actually like is it allows random access to part of the file. Yet, on typical compilation units and header files, it is at least 1 order of magnitude smaller than PCH. It is fast, but smaller. This is one of the things that you get when you pull out the structures that underlie what it is that you're dealing with. Again, I'll be, cutting this theme, like structures. That is what you want when you're programming at scale. And it is easy to process. Like I said, once you get your IFC files, you can write your program in any programming language that allows you to look at binary files and then rebuild what your C++ compiler would see if it was reading this file. It's just a very simple graph-based traversal of homogeneous arrays. Right? So these IFC files, they contain the same semantics information that your original source file contained. They are not meant to replace your source files. They provide a convenient alternate representation of what your source file contains. Your source file requires a C++ compiler. The IFC file doesn't require a C++ compiler. It's not a replacement. It is an alternate representation of the same information. And in one context, you need your source file. In another context, you really don't need the source file. If you already have the information available in a different form, easier to use. Okay. So what is typically in an IFC file? There are a bunch of stuff there. From high-level C++ perspective, you have representations of declarations, representation of types. There are a lot of types. Representation of statements in the body. Now, if you have a function definition, the statement comes as the body of the function. You have expressions that make up, types and functions. You have the names of functions, template arguments, template IDs, and what I call charts. Charts are just parameter lists. Like a template is an entity that is parameterized by a chart. And you have scopes, which, kind of generalizations of C++ notions of scope. And in the IFC file perspective, a scope is essentially a sequence of declarations in a given region. Now, remember, in an IFC file, you don't need to do name lookup because that has already been done by the compiler for you. Okay, so things are quite simple. So this is the first order of things that you find in an IFC file. And then when you dig a little bit deeper and you realize that, there are other stuff up there that you need in order to make sense of the rest of the file. So you need a string table. What is a string table? A string table is just a concatenation of all the strings that the compiler has seen in your source file. Not just the string literals that you have there, but also the names of your, the identifiers and the names of things that you put there, from the compiler's perspective. They're just strings and just put them in a table for retrieval later. You have a table that describes source locations. The Msvc compiler, as you know, is a compiler just like many out there. It's quite old, but still ticking and doing well, and has been using the technology of token streams to implement templates and template instantiation. You've probably heard that the MSVC team has been doing rejuvenation, trying to replace the token streams with parse trees. That work is done, but the token streams are still there for certain constructs that are kind of difficult to get into the parse trees. An example of that would be if you ever heard of the underscore if exist extension to the MSVC. If you don't know what it is, then just forget about it. If you know what it is, you know that it is token based. There is no way you can just make parts out of it because it's token based. So still needs token streams to handle these difficult constructs. And you have pre-processing forms. So pre-processing forms they are part of the preprocessor states, like the conditions that you see in if def and in a conditional inclusion, that kind of stuff. And then you have heaps. Heaps are just sequences of pointers, in some sense, and some look-aside tables for pragmas and other compiler data structures. So, if you from high-level C++ perspective, you have these very nice stuff, and then in order to make sense of them, sometimes you need some lower-level compiler stuff on the side to help you make sense of them. It is absolutely possible to specify these compiler-dependent things in a way that is understood and supported by all compilers. The question is whether compiler writers would be amenable to look at that, but it is absolutely possible. Even though I'm describing the IFC file, which is specific to MSVC today, these notions are quite common to all C++ compilers. Now, get a sense of what we find in an IFC file. The next question, as you design a system, is what are design choices that you're making to build a system? The first and foremost and obvious requirement is that the IFC file ought to represent all of ISO C++. In fact, just representing ISO C++ is not enough. Every single compiler has an extension. So the representation choices must be general, flexible enough to represent not just C++, but a little bit beyond. And also, you want your representation to be a little bit more general than C++ because the C++ committee is not on vacation, right? It's not retired. They're still working a lot. So a lot of stuff coming in, and you want to be able to be ahead of the curve so that the representation choices that you make are kind of prepared. You can't always see the future, but you can make good guesses and be prepared, be ahead of the curve, right? So that's the first principle. Another principle and design choice, that I made was that I want fast manipulation. I don't want something clever. I want something fast. And it is really hard to beat arrays. Vector is really hard to beat when you want something fast. Random access memory, right? So entities are represented in partitions, what I call partitions, just homogeneous table of stuff. And then when I need to reference an entity, I use what I call an abstract reference. And there's some kind of typed index, strongly typed index. And the other design decision that I made was quite early one, was that an abstract reference will be it'll be like a pointer, but instead of having its width variable, it'll be 32-bit. And the reason I set it on 32-bit was 32-bit is already large enough to handle all the set of codes that are thrown at compiler today, like have to be able to compile Windows, Office, and all kind of stuff very fast. 64 bits will make sense, but the problem is when you're building a compiler, one thing that you find out in data structures using compiler is that there are a lot of pointers. So when you make your abstract pointers or references 64-bit, you're just doubling basically the space that you need without actually representing more information. And my practical hypothesis is that 32-bit is way sufficient for anything that is needed. And I will show you why that hypothesis is plausibly true. So an abstract reference is essentially 32-bit value, and it has two components to it. What I call a tag that designates the partition that the abstract reference is pointed into, and then the index parts of the reference, which is basically just the position of the entity in that table. So when you get an abstract reference, the first thing you do is you locate the partition. And once you get the partition, you index into that partition to get the entity. So it is really, really fast. Just to give you an example of things that get done. So you have a declaration, a function declaration, a variable declaration, a field declaration, all sort of declarations, right? You want to aggregate those semantically similar notion of tag into sort. That's what I did. So I have a declar sort that deals with all the sorts of declarations you can have. You have type sort that deals with all the sorts of types that you can have: pointer type, reference type, array type, and non-static data member type, all sort of types. And then expression sorts, which is the sort of all expressions you can have. Like an expression is the shape, right? You have a variable reference, and then have a pointer dereference, and you have an arrow, and plus, minus, that kind of stuff. And a name sort. We don't think about it quite often, but a name in C++ is quite rich. Obviously, you have an identifier, right? But you also have a template ID. A template ID could be, you have a template name, and then you have the template argument list. So the template name could be an identifier, or it could be an operator, or it could be a type, right? And you have a template argument list. The template argument list, things in there, they can just be the name of a constant, the name of a type, or the name of a template, a class template, or it could be a more complicated type expression or more general expression. So a name in C++ is fairly rich, and if you want to process names well, then you need to understand types, declarations, and a bunch of other stuff. So it is quite recursive. Now, concretely, if you use the Msvc compiler today, and then you compile a module interface source file, it creates an IFC file. If you want to look into that IFC file, how does it look like? Well, I think I'm telling you, this is the first time we're describing this, is that the first 4 bytes are what we call a file signature. It tells the compiler, oh, this is possibly this type of file, just like when you have a PNG file or a JPEG file, these binary format, they all have some kind of file signature. And then after those 4 first bytes comes the header. So the header is just some kind of structure that describes what you're supposed to find in this file. So the header, has some reference to other partitions, and the string table is very much important. Without a string table, you can't make sense of a lot of stuff going on in there. And then the header also references the table of contents. The IFC file has the notion of table of content that is near the end of a file. So what does the header look like? So remember, the header comes 4 bytes after, the header starts after 4 bytes into the IFC file. So after the 4 bytes, you get 256 bytes that describes the checksum of the binary file. So if you give something that looks like an IFC file to the compiler, the first thing we'll try is to see if it has some kind of integrity check. Like, does this really sound plausible that this is what was in there and the structures are of the right type of stuff, right? So the compiler will do that. It can take a while to get there, and if you're pretty sure that you have the right IFC files, then you have a compiler option that allows to disable the check. If the compiler ever sees that the checksum doesn't work, then it just aborts, say the file is corrupted and won't do anything. And then the next 2 fields, that's 1 byte each, describe the major version and the minor version. I don't remember exactly which version is out there right now, but if you ever write your own scripts to look at these IFC files, you'll tell me. And then followed by another byte, which is the ABI, another byte that says the architecture for which the IFC is compiled. And then you get a 4 byte that tells you the dialect of the language, more specifically the language version. So if it is compiled for C++ 20, then it will give you the value of __ C++. If it's compiled for some other version, it will tell you that. Now, to get the fun part, to make sense of anything else that follows, you need to get all the string table. You need to get your hands on the string table. So the string table is described by 2 entries in there. 4 byte that tells you the byte offset from the very beginning of the IFC file, from there to a place down in the file where to find the beginning of the string table. The string table is just a sequence of bytes that you interpret as strings. They are 0 terminated string, like in C. And it also tells you how large the string table is. So you have 4 bytes to tell you where the offset where the string table starts, and another 4 bytes that tells you how long is the string table. Okay, and then comes something that's called, another 4 byte called the unit index. So the unit index is a description of what kind of source file that the compiler thinks was used to compile this IFC for. So if it was a module partition, it will tell you. If it was a module primary interface, it will tell you. If it was a header unit, it will tell you. And if it was something else, you get, you don't know. And it also gives you the source path, the file path to the source file that contains the source out of which the IFC file was produced. So that source path is given by an abstract data type, the text offset. It is roughly just a 4 byte index into the string table that gives you the name of the source file. And then follows, interestingly, the starting point of the global scope. All the declarations in the global scope, they're somewhere. And you get an index that tells you, okay, this is a source file. I have a bunch of declarations, and the global scope starts there. Right? That's what global scope tells you. And then you have another 4 byte that tells you the table of contents, which is basically an offset into the IFC file that tells you from this place onwards, you will find the table of content. The table of content is a summary of what is in there. I'll tell you what the summary is shortly. And the summary is just a sequence of partitions, IFC partitions. And you get a number there that tells you how many partitions there are in the IFC file. And then there is one final field that tells you whether the IFC file was compiled for a module an internal module partition. And this, like I said, this is kind of a very strength-based that need to be handled a little bit differently. Most people won't need internal module partitions. So as you can see, you can write a script in any language to look at the binary file and spit out these information. Okay. Now, what is a partition? A partition is essentially a homogeneous table. A partition has a name, and the name is given by a text offset. When you get the string table, you use the offset, text offset, to index into that string table, and that gives you the beginning of the name until the terminating null character, right? And you have another field. The second field after the name is the offset. Where does the partition start in the IFC file? And how many entries are there in the partition? And what is the size of each entry in the partition? Remember, a partition is a homogeneous table. So all entries in the partition have the same size. So with these kind of abstraction, you basically get all you need to start making sense of an IFC file. Okay. So the next piece that you need, and I mentioned earlier, was that an abstract reference is essentially a typed index. It is a 32-bit value that gives you access to an entity. So the first part of an abstract reference is just a tag. It's a value that's given by a source that tells you what sorts of partition this is for. And then the index tells you the position into the partition. So the n here, the n here is the number of bits necessary to describe all the sort in a given sort type. So when I have a declar sort, for example, all the sorts in a declar sort will represent, they're all numerical values. And the minimum amount of bits that you need to describe all those values is what that n is for. So all it is saying is that tag is the bit field that have width n, but of type sort, and then index is of type index and uses the remaining number of bits, 32 minus n, to describe the position. And like I said, this is really, really sufficient to describe everything in practice. Now, so like I said, references, we use them to reference entities. I mean, I have a lot of them. Just to give you an idea here, for declarations, I have a declar index. For type, I have a type index. So for a declar index, the width for the sort is not the same as the width for the type index. Same for expression index or name index, statement index, and chart index and string index. So those are kind of have two parts to their stuff. And then there are these other indices that kind of, I would say they are trivial because there is only one source there. So a scope is just a sequence of declarations. So essentially it's just a number, right? But we make it a distinct type. The same thing for a text offset. All the text, string, and name, identifiers, they go into the string table, and you get a string out of the string table by using the text offset into the string table. And then you read the characters till you hit the null character, right? So words, what are words? Words are very specific to MSVC, I would say. They're the abstraction of things that happen between a preprocessor token and a standard token. MSVC doesn't make real distinction between these two. Most compilers try to make a distinction, but usually distinction is ephemeral. And when we save these things on disk, they are just words. They are not tokens, so we're not calling them tokens. They are words. And sequence of words makes sentences, right? So when you have group of words that gives you a group of sentences, then you've got to associate index to those sentences. So the group of indexes on the right side, they're trivial, and the ones on the left side are a little bit more structured, I would say. So how there are a lot of these things. So this is just a summary, right? In actual practice in the compiler, I have more than 24 of these indices, index types. And how do I get to deal with them in practice without shooting myself over? Well, first, I'm very fearful of implicit conversions, the anarchic implicit conversions that we inherited from C. I'm really afraid of them for various reasons. They happen while you're not looking. So I use templates and distinct types and templates to tame these complexities. Once I get to templates and a lot of types, is that, okay, I'm not going to write a bunch of templates without having constraints on them. So I'm going to use concept. Right. Okay, I can use concept only if I get the right structures, which is why we did this whole exercise so far. When you look at all these zoo of references, you can basically segregate them into two camps. So what I call an algebra is just, an index, here I'm using universal algebra terminology. And here I have to apologize for reaching out to my mathematical background. I'm trained as a mathematician and writing programs as a programmer. So when I have difficult problem to solve, I go back to math because it is very hard to argue with logic. So a few typos here, missing semicolons. So an algebra over a sort is either you have a unilevel sort or you have a multi-level sort. So unilevel sorts are essentially the ones that I can define by enums. So you have an abstract type called index, which is just a 32-bit integer that's reference for all index types. So if I have an enum and it basically has the same underlying type as index, I consider it unilevel algebra type. It's not the most accurate specific definition, but it works for the task at hand. And then the one that is interesting, the multi-sorted algebra. So again, I require that they basically have the same representation as an index, but because this is quite structured, I need at least two operations from this in such time. It has to have the operation sort. Give me the sort. Which kind of sort is this for, right? And what is the index into the partition? So remember, the sort will identify the partition, and the index will give you the position into the partition. So when I have a multi-level index, like Decla index, when I call sorts on the Decla index, it will tell me whether the Decla index is for a variable or a function declaration or a class declaration or a type def declaration, that kind of stuff. That's what we're talking about here. So interestingly, just having these three concepts, believe it or not, was the only necessary abstractions that I needed to write the templates that deal with all sorts of things in the compiler as they relate to modules, and being able to directly express these notions through concept is first, a good documentation. I don't have to resort to Sphine, and it helps my colleagues that were helping me, like Cameron Da Camera or John Caves, who helped me a lot, implementing modules in the Msvc compiler. I started using Sphine before the Msvc compiler got concept implemented, but oh boy, don't ask. it was terrifying. And the module group was the first to start dogfooding concept in the compiler when it was implemented. So this is an example of the Msvc compiler eating its own dog food as it's delivering it to you. So conceptually, this is how it looks like. Structurally, like concretely, how do they look like? Structurally, all these type index and decal index and expert index, they all look very similar. And when things look very similar, you know you have a template. So the way I define this thing is by inheriting from this Uber template class that I call index-like-over. It's essentially giving you an index type over a sort. That's what it is for. So if you give it a decal sort, it will give you a decal index. If you give it a type sort, it will give you a type index. And if you give it an expert sort, it will give you an expert index back, and so on. So for the 24 index type, that I decided that they need to be distinct type because I'm very fearful of the implicit conversions. This is how it is done, and it is just half page of code like this. And then if you want to know how this Uber template, for index type looks like, here is a definition. This slide is a little bit crowded, but the actual things are quite simple. So here you have a nested type called sort. So this over type is parameterized over the sort type. So just introducing that sort type nested name there as an alias. Have a default constructor that's nothing. And then here is an example of me being fearful of of implicit conversions. So when I'm constructing an index out of a sort, a position, I don't want to be able to just be vulnerable to some implicit conversion, making a mistake at night when one should be sleeping but working late. I don't want to be vulnerable to implicit conversion. So here, the template that says same as UN32T is explicitly saying that the type of the second argument here, whatever it is required to be exactly UN32T, not convertible to. No, exactly like that. So that way, I make sure that when I write a constructor like that, I'm exactly putting the right type. I'm not putting an expression of a type that will implicitly convert to that. It's exactly doing that. So this is another example of using concepts to help you introduce safety, increase safety in your software, right? And then you have a couple of accessors, sort and index that just return the things that are used to construct the index. As you can see in the private declaration, you can see that the index and the tag, they are complementary in terms of width. Together they make up a 32-bit value, and tag precision is just some context for template variable that gives you the precision, the exact number of minimum bits needed to represent all values of S. Okay. And I just realized that on this slide, I'm using just about everything that I've ever worked on in C++. Context for variable, variable templates and a bunch of concepts and a bunch of other stuff. Curious. So now this is the concrete structure that is used to implement these concept that I showed earlier. This is just showing you that this structure that is used to declare these distinct types satisfies the constraint of multi-level type, and can add a bunch of other types later. We know through the concept that we have guardrails and we want to be shooting ourselves in the foot. Okay, so far so good. Now, if I want to deal with a specific sort, like imagine I have a decal index, and so a decal sort is a sort that encompasses all the declarations that are possible in C++. So you have a variable declaration, you have a function declaration, you have a parameter declaration, and so forth. So how you present a function declaration is very distant from how you present a parameter declaration, right? A parameter declaration has a default argument. A function doesn't have a default argument, but a function parameter has a default argument, and the structures are not the same. So for each specific search, you have an implementation of it. So imagine I have roughly 27 sorts of declarations in the Msvc compiler. So I'm going to have 27 structure that implement each of those things, right? And it can get overwhelming. So if you want to deal with that kind of complexity, you want a template. Once you get a template, you better have constraints on it so that you don't shoot yourself in the foot, right? So how do I deal with an index type for a specific search? So the way I think about problems every time that I got to solve an interesting problem is I go back to, my roots, math, logic, and algebra. The way I'm looking at these indexes is that I have a base geometry. And then on each point in that geometry, there are some stuff that are planted. Those are the indexes, right? So call those things fibers. So in geometry, I have my base curve. Then at specific point here, I have fibers. So you can see that we have what we call a fibered manifold. And once you have that kind of thinking, a lot of, from my perspective, a lot of analogies and thinking just unlock and allows me to write code. I don't want to write a lot of code. I just want to write the right code, right? So turning this into concept is really simple. So basically, a fiber over something, right? You have two things here. You have the base, and then you have a fiber over it. So a fiber over the base, since essentially you have an implementation of an index type, right? It has to be multi-level. And then that type has to tell you that somehow, it relates to the fiber. So you get all algebra sorts, which is the compile time value that surfaces something from runtime so that you can actually manipulate at compile time. Right. So this is basically actually the compiler code, and I think I commented that that other part of the constraint just to be less pedantic about it. Now, I've shown you a little bit of, I'll say, hardcore internals of how the IFCs are implemented and the structures behind. But once you understand the principle behind, you can quickly realize that, hey, manipulating these things in a scripting language or anything else other than C++ without requiring C++ compiler is relatively easy. Like, you just need these concepts in place. They allow you to decompose your types, problems into smaller domains and then search for commonalities. And then just use your usual templates to handle them. You can have your templates in Python or Ruby, and you know how they work. So now that you've seen that, where do we go from here? This is the first time that I'm talking in some details about how the IFC files is working. What I would really like to do is actually bring this specification, so this description, not this specification, this description to the C++ community. So the plans is that early 2021, like in a couple of months, I will release to the C++ community a draft specification of what the IFC file are. The intent here is to work with the community to evolve the IFC specification to something even more awesome. That is useful to a much larger set, set of people, to the entire C++ community, ideally, and also that is not specific to the Msvc compiler. Okay, so the intent here is I'm really seeking help, collaboration from people interested in pursuing this kind of project in defining a module format, binary module format that is potentially used by all major C++ compilers. Of course, I will try to involve SD15, the tooling study group in WG21, and that will work to the extent that they are interested. If they're not interested, that is fine. Here, I'm really, really looking to the C++ community, not the committee, the community. And I very much want to work with the committee if they're interested. If not, then I'll just work with the community. And then, of course, develop a set of APIs and libraries that allows you to construct, manipulate these data structures. So the IFC is ideal for on-disk storage, right? But when you want to do the manipulation, you have to read this thing into memory. You need the data structures. And as I said earlier, the IFC files structure were developed based on principles very much similar, same as the IPR. So I want to be able to have libraries that allow you to construct IPR data structures out of the IFC files and vice versa, right? And then also, bring in more IFC-based developer tools that allow people to do semantics-based analysis of, source files without requiring at all time a C++ compiler. Really, this is an opportunity to do something like this. I'm not trying to put C++ compiler developer out of business. I am one of those. Okay? You will always need them. You can't talk about C++ programs without having C++ compiler. The goal here is not to put them out of business. I can't. And that's not close to anything they want. What I would like is to open the pipeline to a wider set of people who would like to do work with C++, interface with program, semantics-based analysis, but are lacking the tools to do that because that would require being a compiler developer in the first place. C++ compiler developers, you can probably, lock them in a single room. If you don't trust me, go to a C++ committee meeting. They are all in the co-working group. It's a tiny room. So at this point, I'm ready to take questions.
So you talked about plans for taking this in 2021. Can you talk a bit more about this, about details? What are your visions for this?
So, details in terms of execution or?
Yeah.
Okay, so what I'm looking for is, the first thing is just release the draft of the IFC spec. Right now, it is on my machine, and that's not a good place to be. Well, it's also on the corporate repo, but that's not. What I meant is it has to be in the hands of the community, right? For people to look at it, and I don't pretend to have the best or the most beautiful design. So I'm looking for feedback, and for that, they need to have the concrete things. I suspect a good way to do that is to create a GitHub repo and put the spec there. They're just a bunch of LaTeX files, and invite feedback in terms of pull requests or discussions on how to improve things, and then take it from there. The idea is that we all agree are goods we need to do and we need to improve. Then work with the Microsoft compiler. I'm hoping that the Clang community and the GCC community eventually will join us. All the compiler writers are at different stages of the implementation of modules, right? Mm-hmm. I think I read last week that GCC is reviewing the patches for Nathan Sidwell's implementation in GCC. Now, crossing fingers, and if everything goes well, that will go into GCC 11. So I think the focus for GCC community right now is to get GCC implemented. Once that is done, the next level I would like to engage the community is, hey, there is an opportunity here. Is there anything that we can do? Like, you don't need to use this representation as your de facto internal representation, but can we have a switch or something that allows those people who want to also produce that format so they can work with it? So, this format doesn't need to be the representation of a one specific compiler detail. Like the IPR, for example, is compiler neutral. It is not what is used in MSVC, but we are able to build IPR out of the IFC, right? So now, as long as we know the set of semantics information that need to be preserved and ways to preserve them, we can get that. So that's the first step. Get the spec out, work through like iterative design. And the next phase is, instead of having 5 billion C++ developers each writing their own script or libraries to fiddle with these data structures, it would be much simpler if we actually had a set of APIs or open source libraries that people can just download and use them to read these files and do the manipulation, and not having to think about how things are actually read or written on disk, right? Just like you can do photo editing without having to know the exact detail of how PNG format works, right? So I would like to see the C++ community in that kind of position.
Okay, one question from the audience: is your code on GitHub?
Which one?
For the IFC files.
No, so the IFC file, the libraries
what code will be on GitHub?
The IFC spec and the libraries for reading the IFC will be on GitHub. Right now, what is on GitHub is the IPR, which is internal program presentation. It's a work that I did with Bjarne 15 years ago, more than 15 years ago. And the first compiler that actually connected to that data structure, out of which I could get those data structures, was GCC. Then there was Clang, and then there was EDG. But GCC was the first that I used to design that library.
Okay, there's another question regarding C++ 17. What do you propose how to structure C++ 17 code today so that you have the least work tomorrow using new C++ features like modules?
That's a very good question. The first that comes to mind is avoid reliance on macros. Like, you've heard this from me a lot, but it's really important. So C++ 17, everything we did, is with header files. So if you want to transition to C++ 20 using modules, you probably either want to go through header units or directly to named modules. If your header files behave very well at just really interfaces, moving directly to modules are the best recommendation. So if you take the hygiene of keeping your header files simple, you get that. Header units are transitional mechanism. I don't really recommend them because if the goal is to use modules, going through header unit is like when you're using C++ as C with classes, right? You still compile with C++ compiler, but you don't get all the benefit that you can get if you directly use the right abstractions.
So there's a question from Hannah. Do I understand correctly that you are proposing one common module format for all C++ compilers? Is this the next step, common package format?
Okay, so what I'm proposing is a common format and set of APIs that I want to develop with the community, as opposed to Gaby slept, thought, dreamt of something and came with something. I want to do this with the community. Now, come with that. I'm not saying that this format has to be the data structures that every compiler uses internally. Just that these compilers be able to produce those data structures. If a compiler decides that, oh, yeah, that thing is nice, but they have a better idea, that is fine, as long as they enable the generation of this common format. Yes. So is the next step common packaging? I'm not working directly on package just now, so I don't know how to answer that question. There are people who are working on packaging, and from time to time we talk, but that's not my...
Okay, that's not your goal.
Yeah.
Understood. Are modules now fully supported in the latest Visual Studio version as defined in the current C++ standard? What are the current limitations?
Okay, there are... modules implementation is feature complete in the MSVC toolset, right? And then there is a support for it in the IDE. There are a couple of outstanding bugs. No, those couples are assigned to me. I can talk about it. So the deduction guides. I think the standard doesn't say that you can export deduction guides. Like, it's not part of the spec. In practice, if you want to support standard library headers as header unit, you need to be able to export deduction guides. So the actual fixing of the bug is not complicated. It is just Gaby finding time to do it, which Gaby is going to do this afternoon or tomorrow morning, because a lot of people are waiting on it. There is another obscure bugs that I heard about last week. But they are bugs. They are not absence of facilities that the real limitation. The IFC compiler has also been implementing modules, and they are able to consume the IFC file I just presented, and then provide IntelliSense support through that IFC file. So you have at least 2 compilers now in production that have support for this.
So can you build your own reflection engine by manipulating the IFC file?
Yes, you do. The thing you don't get is what people call static reflection. Like you can't in the same source file do these manipulations and then have the result compile right away. However, I do expect that a good reflection facility will need data structures very similar to what needs to go into a module binary file, whether it is an IFC or it is the one that's used by GCC or Clang. They will need facilities like that. So, all these needs are coming from different angles, but they are converging. You can do introspection and marshalling, as I explained in the talk.
Will IPC files also be consumed by the compiler so that we could run the compiler, transform the IPC with scripts, then run the compiler on them again to generate code?
We used to support that at some point. I don't know why the support for it rotted, but yes, in the future, that is something that I like to get done. I think that should be done largely outside a compiler. I think that's probably why I let it rot. But yes, it is completely possible. The reason is very simple. The IFC file needs to represent all of C++. Right? So, all informations are there. So you can just point the compiler to that stuff and tell me generate code from it.
So you could use this for serialization, deserialization framework, generating code from IFC files?
Yes, absolutely. That's part of when I mentioned Marshall. When I say marshalling or doing distributed computation, these are different words, probably common, like serialization, deserialization. Yes, exactly.
Does your proposal open up the possibility for new form of C++ metaprogramming?
Yes, it does. And to my mind, it is complementary to the work being done today in the study group on metaprogramming and generative programming. Like they're very much complementary. Remember, language design is library design. Sometimes you get to experiment with libraries to get a sense of what the right interface needs to be from the language perspective. But the functionalities, you get to implement them as library.
Okay. So there was one more question, like, should you learn other languages to support Remo hangs kind on me right now. Oh, there's another question. I can read the question to you now. Should C++ people learn other languages to help others?
To
help others.
I always think it is a good idea to know at least 2 or 3 programming languages. It helps thinking. It gives perspective. If you get the opportunity, I'll strongly encourage you. And if you don't get the opportunity, try to find time to learn some other language. That is not like C++. The interesting thing is learn something that doesn't look like C++. That gives you perspective. Programming languages actually affect how we think. So learning a different language brings new perspective.
So you're going to release a specification?
Yes.
And is there also going to be code released with this to read or handle?
So the spec will come first. The spec will come first, and then the readers and the writers will follow. The reason why there is that delay is I would like to be able to get early feedback, turn it around so that we hit ground on the right foot.
So what's your future vision for IFC as a format?
Good question. The bare minimum that I would like to get that, I think we will be way there, is just have at least 3 or 4 compilers support this. Like, if they hate IFC, that is fine, but let's have something common. Like, let not say that this is not perfect, therefore we can't do anything. Let's not say each compiler has its own particularities, therefore we can't do. Like, I refuse the theorem of incompetence. It is complicated, so we can't do anything about it. No, that I refuse. But I very much believe in giving people something to play with first, and then even the naysayers, right? And then see how they like it. I remember 15 years ago, or more than 15 years ago, 2003, when I proposed constexpr, the very first presentation in Kona, October 2003. I think the compilers basically explained to me that it was kind of insane. It was impossible. And it took hard work to get in there. Even when showed concrete implementations, people still wouldn't believe it. The specification had to be restricted so that it could just barely get in there. Once you get in there and people start using it, oh yeah, we want everything. Sometimes I'm the guy who has to stand in front of people. No, don't do that. Like, I really love constexpr, but don't do that. Like, so I feel like I'm in the same situation again. I would love to see the IFC like an alternate representation, semantics representation of C++ programs, and so that you can You can manipulate. Compile time, runtime, doesn't matter. But you don't need all the time a C++ compiler to do that. Now, just imagine how the advent of Java class file actually opened up a lot of possibilities for the Java community, right? So think that we have the IFC. The next phase, very natural, that comes with the IFC, is actually you have some kind of formal specification of a C++ abstract machine, right? So now you have a platform for people who like to experiment programming language to target the C++ abstract machine. Like they don't need to write C++ with C++ syntax, but they can run C++ if they target the C++ abstract machine. But you need to give them a specification, right? And so that's one practical use. Another one is it's actually will help us in the committee in specifying the core language. Like it brings some kind of, it's a forcing function to be clear about certain aspects of the language that we all, okay, I'll reflect. Yeah.
There seems to be another type of generic binary interface from Kenny K. Are you familiar with this, and what would be the difference to IFC?
Okay, so I suppose it doesn't matter who asked this question. Yes, Kenny Kerr's group is working on a meta description of the Windows SDK so that you don't actually get to have to deal with Windows.h anymore. It is a meta description of the API, a bunch of other stuff that is very, very modules friendly. At this stage, it is still in development, in experimentation phase, but we do have communication channels. I guess that's what I can say at this point.
Okay. Why is a common format between toolsets so important?
Because we're dealing with the same language. On my platform, I have 3 compilers. I should probably have 4, but I have 3 compilers. So, and I have just one program. If I want to test my program with 3 compilers, and the 3 compilers each generate their own format, then I have to deal with 3 out of just one program. I have to deal with 3 different formats if I have to do anything interesting with that information that comes from that single source file. I think that is insane. There ought to be a way to be able to deal with that, to manipulate that data that comes from just one single source file that shouldn't depend on the compiler. Like, I understand why it can be a kind of work for implementers, right? I'm one of those. But like I said, you can lock implementers on a planet in a room. Just go to C++ Standards Committee meeting. There, right? But we have more than 5 million of C++ developers. There are more users than people who write the compilers. So what I'm saying is, for the benefit of the community, this is a technology enabling opportunity, right? For the benefit of the community, I'm inviting my fellow implementers to, yeah, it's painful, but it's not that painful if we do it properly. And then give this to the community. So it is important to me only to the point that I want to help the community. If the community says we don't want your help, that's also fine. A concrete way to measure that is I release this and I have no feedback, or the only feedback I get is go do something else. Right.
Do you plan to have a newsletter or some additional information distribution on this? Will there be like a newsletter available? Is the question.
So there will definitely be so when the spec becomes available, I will write a blog about it. I'll try to write some kind of detailed rationale or something, document that goes with it, explaining the design choices and how they affect some of the consequences, how they affect things. I think these design choices that I keep either in my notes or somewhere else, they tend to be useful over the long run. When not shared with the rest of the community, then we lose focus. So there will definitely be more communication about this.
Okay. Do modules work with managed C++?
At this point, there have not been any explicit work to support managed C++ or other Msvc extensions. The focus of the work has been on standard C++, and some degree managed C++ is it's already .NET and
Will different compilers generate different IFC files for the same source code?
So it is possible that a compiler might generate slightly different, but in terms of when you're looking at the semantics information, no, they will not, because they are all making the same semantic determination, unless there are two compilers who happen to completely diverge on the interpretation of the standard. But if they have the same interpretation, they will give you the same information.
And at least for now, I don't see any more questions. So if the audience wants to ask more questions,
I'm here as long as.
Yeah. So if you want to write a blog post about that, or I'm happy to host you in 2021 for this, of course.
Thank you.
I found it very interesting, and I found it a very interesting vision. What about ABI? Does ABI play any role in this, or?
So the ABI in most of it plays a role when you start doing cross compilation, right? Not only cross compilation, but you're getting how should I put this? The Msvc compiler allows you to specify command lines that change calling convention in the source file. Mm-hmm. So when you create these IFC files, you want to be able to say, actually, it is only for this kind of ABI. And if someone is importing it, then unless you can generate some kind of thunk to bridge the gap, you can reject. So the amount of information that ABI plays a role, but not as strong as the target architecture or others. So this is one of those places where when you go open source, give me feedback. What do you think should be in the header, and what do you think should be in secondary section of the file, so that when people open, they're looking at the headers, they just get the primary information that is needed, and then only look at the secondary aspect.
How will this play with Google's variant of modules in Clang? Because they already have been using it many years internally.
Yeah, so I'm not the expert on, I've worked with the Clang compiler, but I'm not the expert on Clang. So Clang has the notion of PCH, PCM files, serialized data structure, and that they used to represent, Clang modules, and now they're using slightly to represent C++ modules, and a slight variation of it for PCHs, right? So when it's kind of same format, but slightly different information inserted in there. The IFC is completely done from scratch. I do expect that as we start writing these libraries that will work with other compilers, we will be able to do the conversion and either augment the IFC or look whether client wants to augment the PCM files to contain some other information. But I do expect some interchangeability. I can probably mention this other experiment that another team is very closely in my org is also working on related. The code analysis team, for example, has been experimenting building the IPR data structures. The IPR on GitHub today, mm-hmm. They are able to build IPR out of the Clang AST. So this is not science fiction. This is not science fiction. They are doing that, and they did that experiment just to give me feedback in terms of where the gaps are, and the gaps are not that significant. So that gives confidence that, if I use the same principles at IPR for the IFC, I'll get to a place where it is possible, for example, to interface with Clang. I would really love to do the same thing with GCC. Like I said, remember, GCC is the first compiler that I connected to the IPR. Okay. I really, really love to have that from GCC too.
Is there a way to determine if two IFCs are isomorph?
Yes. That's mostly just graph-based isomorphism algorithm. Very simple. Not the ones that are undecidable.
I have a simple question. Does the IFC file format contain checksums that you can check for the correctness?
Yes. So the after the 4-byte that gives you the signature of the IFC file, the next 256 bytes are a checksum that you can actually use to check for integrity.
And I don't see any more questions, but this was an awesome opportunity to talk to you and to just hear these ideas and see where we're going with this in long term. I'm really happy to see where we're going with this in the future.
Thank you. I still remember that question you asked me. I think it was 2015. I can't remember. 2017. I can't remember. When you asked whether modules will make it in C++ 2020, and I couldn't give you a straight answer. That was at TPPCon.
Yeah,
because I couldn't predict the future, right?
But yeah, no, that's so I don't know. You probably don't know about that. I in 2016 I talked to Bjarne what he would think about you keynoting.
Oh,
and he said, well, yes, that's a great idea. But he also said, let's wait for C++ 20. And on the other hand, the other question I usually asked, which was because I kind of understood that, at least at that time, basically, back then, macros was one of the pain points for at least for other people to understand how modules will work. And so I mostly asked that question, and you gave talks, and that's kind of how we got to know each other.
Yeah, and so now that we have the implementation, and I'm very excited about what's going on in GCC, I'm hoping, crossing my fingers, that it will get in C++ 11. Now, so the build system aspect, which is the other thing that is very important, right? It's not just it's good to write a thing, but if you can't run it, so the MS build folks, Olga, has done tremendous progress in adding support for modules. We are talking to the CMake folks to add support for Msvc's compiler for modules. I got into contact with the Mason folks. They mentioned that there was a bug that was blocking them, but I think that bug was fixed. From what I understand, there was a bug from the IDE. I think it was fixed. but I haven't heard anything since then. I'm really hopeful that they're making some progress there. I know Nathan Sidwell has been trying to define some kind of server protocol for builds. The Msvc compiler doesn't do that today because we have been trying to keep the compiler out of builds business. The reason is very simple. The toolset supported by a lot of build systems. Some of them you haven't even heard outside Microsoft walls. So which build logic are you going to put into the compiler? So we want to keep the compiler out of that business, but define some kind of protocols to allow people to use the compiler to achieve a goal.
Is IFC integrated or into DLLs, or how is there a relation to DLLs?
Okay, yeah. So as of today, the IFCs are not embedded into DLLs. However, as feature evolution, like very close feature evolution, we would like to be able to embed the IFCs in DLLs. And the reason is very simple. Sometimes if you try to do like runtime introspection, you need these kind of data, right? You can put them on a separate file, or you can embed them in the data segments that the system used to run the program, right? The other thing is, I would like to be able to bring more safety to some operations that we do today. Like when you say on Linux, you say DL open, right? And then you say, DL sim and give some symbol. We don't pass a type, right? We get something back. Either we treat it as a variable, as a function, and we cross fingers. What if we can actually embed the type description that was available at compile time into the executable? And then when you say DL sim, you can actually pass the type description to it. And then when it finds the symbol, it tries to match whether the type is the same before returning anything to you. That is increased safety. It doesn't give you complete safety, but it is much better than what we do today. You open the file and get some address and then cross fingers that it is the right function, right? So there are a lot of system levels operation like that we do today that we can bring more safety to if we can only embed these rich type descriptions there. And that goes back to what I was saying earlier, which is that we use C++, but when we want to talk to other systems, we are not using the richer, safer, part of C++. We downgrade ourselves to a very low level, the unsafe part, and then do that, and then we cry that system is not safe.
So right now this is implemented for Msvc.
Yes.
But I do know you have a history as a GCC maintainer. So
yes.
Can we expect this being also available for GCC at some time?
My hope is yes. Whether it will be done by me personally, I cannot commit, but I do hope that will come to be. So Microsoft is very much interested in Linux, as you know, and in GCC toolset. So if there is any way we can work with the GCC community to get this into GCC, I would love to. I'm really open to, there is no secret here. There is no, everything is, the only reason why this has taken so much time to get out is just, I have been on the deluge of things. And, I know the ID team is not very happy with me because they have been waiting on the spec so that EDG can implement the stuff, right? And they're like, yeah, but you're doing those stuff in the tool set. Why can't we have it in the IDE? Okay, I have to do it. And so at night time, I'll write the spec, but I also have to sleep.
I know that problem.
And so
do you envision runtime recompilation optimization in C++ based on IFCs?
Yeah, I expect this will enable. So this is enabling technology. Now, with the IFC 5, what you have is just a much simpler representation of the same information that you got in your C++ file. So at the runtime, you can say, okay, based on what I've seen running so far, the data that I've gathered. So I'm going to make a different design, decisions on optimization, right? And then just do those kind of jigging on the fly based on this kind of profile gathered. You gather some data at runtime and then optimize differently. There was a paper by Hal about jigging C++, and I'm like, yeah. That's something I can do with IFC. I'm not doing it just because I don't have time, but if I have free time, that's something I'll do. I know how to do it.
So would technologies like ThinLTO, which we had a keynote about yesterday, profit from this, and generally Optimizer have maybe new ways of understanding the code? Yeah.
So the IFC files come into the C++ discourse through modules. So people, when you think about it, this is a module builds artifact. And they're like, okay, but that's something you should keep there and you shouldn't do anything else. But that conclusion is wrong. From my perspective, the right conclusion is, okay, it's for modules, but it can represent all C++. Why can't we just use it for the other stuff that we have been waiting to do? Right. I think for me, that's what a community should be asking.
And how do you package dependencies?
In the IFCs? So if you have a modular interface and that imports and then re-export, and we put some references there. The IFC, as I described in the talk, as of today, can only describe one unit. However, the spec that I'm putting out in 2 months will make space for actually having an archive there. So when you have these references to the other IFCs, you can package them. You have coherent reference of IFCs, as opposed to, there's a bit here, there's a bit, another one is missing. Like you package everything as just one single file. And then the references are just and that enables the packaging of the dependencies.
So, I have an interesting question here. So, could this, in theory, also be used to generate something like OpenCL CUDA from pure C++?
Yes, absolutely. Yes.
Okay.
So the C++ abstract machine is sufficiently high level. Right, and the IFC is trying to keep, and the app here are trying to keep all the semantic information and retain a high-level description so that you can target any computing device. Here, if you want to run OpenCL, yes, you can generate from it.
That sounds very interesting. So I don't see any more questions, and we've been now going for almost an hour with the Q&A.